We are going to talk about thermal physics, thermodynamics. There are certain parameters that we should know, certain terminology, but equal terminology is not that old. You already know it, but in general I have just listed few terminologies. I'm not going to go through them in detail, but in general আমরা যখনই থার্মোডাইনামিক্সের ব্যাপারে বলি তখন we are going to consider certain parameters which are actually called as the state function. So state function is important, and in this state function we basically have something which we call as pressure, and eventually we are going to see that how we actually use it. Sometimes we might see that the pressure is constant, and then we will basically call it as an isobaric process. Sometimes we have volume which may be constant, so we call it as isochoric process. Temperature constant is something which is a very important parameter, আর এই প্রসেসকে আমরা বলি আইসোথার্মাল প্রসেস। তারপরে এর একটা নতুন জিনিস যেটা আসবে এটা হচ্ছে ইন্টারনাল এনার্জি। সো ইন জেনারেল হোয়াট হ্যাপেন্স ইজ when we are basically talking about gas molecules, okay, or we are talking about something which is actually affected by temperature, the molecules are also affected by the same. It has got some kinetic energy and potential energy, আর এগুলো সব পার্টিকুলার যদি আমি টোটাল এনার্জি নিয়ে নিই দেন ইট উইল বেসিক্যালি কনস্টিটিউট হোয়াট উই কল অ্যাজ দি internal energy of the system. Okay, and then we are going to come across certain technical terms like enthalpy, entropy, and so on. So enthalpy is, if we want to see the total content of the system at constant pressure. Now in general, whenever we are considering a pressure, it is being affected by a number of factors like internal energy, pressure, volume, and so on. তো এগুলোর মধ্যে যে ইন্টার রিলেশন থাকে, ইন্টার রিলেশনে কিছু টার্ম আমরা পাই যেটাকে আমরা বলি, there is one which is called enthalpy, which you can see is connecting the internal energy, pressure, and volume. Something which you call as Gibbs free energy, which is again connecting temperature, entropy, and enthalpy. Okay, entropy ke amra s দিয়ে denote kori. Entropy is also included in your second law of thermodynamics. That is also something which we are going to study, and so on. So Helmholtz free energy আছে আরেকটা টার্ম, সেটাও আমরা পড়বো. So those things are there. So these are certain terminologies which we can actually think and we'll learn, okay, later. Apart from that, specific heat capacity, thermal heat, only heat capacity, these things are also there. Okay, so in thermodynamics, what happens is there are certain things that we are going to use. Okay, these are some technical terms. That's why like I'm just considering this in general. For example, the first thing which we call is actually called a system. Okay, so whenever I say a system, let's say we have got some kind of gas which is actually inside a cylinder, trapped in a cylinder, and we are applying some pressure. Okay, and then we know that the volume will change, it will compress. If we leave it, it may eventually expand and the volume will increase. So these kind of things are actually called as a system. So eventually in the future, whenever I say that this is a system, that means I'm basically considering a system or a part, okay, where we are going to do the study of thermodynamics. Ideal condition থাকবে, many a times we can say we are keeping the temperature constant and so on. সারাউন্ডিং হলো, ধরো আমার কাছে একটা গ্যাস ইন আ সিলিন্ডার আছে, এর বাইরে যেগুলো যে পার্ট আছে দ্যাট উইল বি নাথিং বাট দি সারাউন্ডিং. So sometime we say that this cylinder, okay, is interacting with the surrounding. Sometimes we will say that no, there is no interaction with the surrounding. যদি interaction with the surrounding না থাকে, ধরো আমি এরকম একটা সিস্টেম নিলাম, and if I basically say that this is my system, so the gas will be trapped somewhere here, and this is my surrounding. Now এরকমও হতে পারে যে the system will actually interact with the surrounding. If it interacts with the surrounding, we basically say we have got a glass of water, hot water. Okay, তাহলে interact with the surrounding, because glass of hot water eventually will cool down. তাহলে এটা সারাউন্ডিংয়ের সাথে interact করছে. এখন যদি আমি ধরি একটা থার্মাল ফ্লাস্ক, থার্মাস ফ্লাস্ক, অলদো প্র্যাকটিক্যালি থার্মাস ফ্লাস্ক অলসো গেটস কুল ডাউন উইথ টাইম, বাট ইন জেনারেল আমি বলি একটা পারফেক্ট থার্মাস গ্লাস মানে ভিতর থেকে কোনো হিট বাইরে যাবে না, দের ইজ নো এসকেপ অফ হিট ফ্রম ইনসাইড টু আউটসাইড. দ্যাট মিনস ইট ডাজ নট ইন্টারাক্ট উইথ দ্য সারাউন্ডিং. সো দিস থিংস উইল বি দেয়ার. So boundary is also something like that. Like for example, if you basically consider a cup or a glass of water, so in general when we take this and if it interacts with the surrounding, we basically say it has got a diathermic wall. তো এই যে ওয়ালটা হবে এটা হবে ডায়াথার্মিক, মানে একটা গ্লাস যদি নিই, গ্লাসের মধ্যে জল থাকবে, অ্যান্ড দেন বেসিক্যালি উই কল ইট এজ ডায়াথার্মিক ওয়াল. ওকে, just write down D. But in case there is a glass, or let's say there is a thermos which does not interact with the surrounding, তার মানে ভ্যাকুয়াম ফ্লাস্ক ধরে নাও, there is no escape of heat from this, we basically call it as an you know adiabatic valve. This is basically called an adiabatic valve. Adiabatic valve. So this is an adiabatic valve, does not exchange anything with the outside world, and this is a diathermic valve, which will exchange some heat with the outside world. So the boundary will decide whether it is diathermic or adiabatic, whether there is a heat exchange with the surrounding or not. Okay, so we have got something which we basically call as process. Okay, it may be an isothermal process, it may be an adiabatic process. We are eventually going to look into that. Okay, next thing which is important is basically called as equilibrium. Equilibrium মানে basically ধরো আমার কাছে যদি একটা box থাকে and there is some gas which is there, so maybe there are some gas trapped here and so on, আর এই জায়গাটা পুরো খালি, তার মানে আমি যখনই এই পার্টটা খুলে দেবো, মেবি আই অ্যাকচুয়ালি আই এম হেভিং হিয়ার অ্যান্ড আই এম ওপেনিং দিস, দেন দিস গ্যাসেস উইচ আর দেয়ার উইল ইভেন্চুয়ালি ফল ইন্টু দিস রিজিয়ন until and unless there is equal concentration of gas on both the sides. This is called equilibrium. Okay, the equilibrium শুধু ভলিউম বা অ্যামাউন্ট অফ গ্যাস নাও হতে পারে, ইট মাইট বি এন ইকুইলিব্রিয়াম ইন প্রেশার, ইট মাইট বি এন ইকুইলিব্রিয়াম ইন ভলিউম, ইট মাইট বি এন ইকুইলিব্রিয়াম ইন টেম্পারেচার অ্যান্ড সো অন। ওভার টাইম মানে অবভিয়াসলি আমি যদি একটু টাইম দিই তাহলে এই গ্যাসগুলো এই পয়েন্টে যাবে, আর গিয়ে দূর থেকে ইকুয়াল কনসেন্ট্রেশন হয়ে যাবে। সো দিস ইজ হোয়াট ইজ দ্য আইডিয়া অফ ইকুইলিব্রিয়াম ইজ। Now something which is very important is the process that we are actually going to talk about. So chatta process ache which are very important. Okay, and let's take one by one. Okay, the first process which will be important is actually nothing but the isothermal process. Isothermal process. Isothermal process এ কি হয়, isothermal thermal মানে it's related with temperature and heat, এখানে আমার টেম্পারেচারটা কনস্ট্যান্ট থাকবে। তাহলে if a system goes from, let's say, volume V1 to V2, there is no change in temperature, the temperature will always remain constant, and this is called an isothermal process. The second process which is there, which is called an adiabatic process. Now this is very interesting. এখানে adiabatic process আমরা শুনতে মনে হচ্ছে মেবি টেম্পারেচার কনস্ট্যান্ট থাকবে, বাট নো, এখানে টেম্পারেচার, প্রেশার, ভলিউম কিছুই কনস্ট্যান্ট নাও থাকতে পারে, বাট দেয়ার উইল বি নো এক্সচেঞ্জ উইথ দ্য সারাউন্ডিং, মানে যে টোটাল হিট যেটা সিস্টেমের ভিতরে সেটা will remain constant. That means there is no exchange of heat with the surrounding. For example, if you are basically considering this thermos flask that I'm বললাম, this is a thermos flask and it does not exchange any heat with the surrounding, there is no interaction with the surrounding, তার মানে the amount of heat which is there inside the box will remain, okay, and it's not going to escape the system, but inside the thermos there might be a change in temperature, pressure and volume, total heat টা same থাকবে. So this is basically called as adiabatic process. Next is called isobaric process. This is also very easy to remember. If you look into this term bar is the unit of pressure. Okay, bar is the unit of pressure, and that's why when we say isobaric process means we are going to talk about constant pressure. তার মানে আমি যদি একটা সিস্টেম নিই যেখানে the pressure does not change although the volume and temperature might change, this is basically called as an isobaric pressure. So many a times if you basically have a wall which keeps on expanding, as you keep on inserting gas inside it, this will expand হবে মানে volume বাড়বে, right? But if we are going to give some additional pressure from outside, we might be able to keep the pressure constant. Okay, so this is basically called as an isobaric process. And then আমি বললাম যে temperature constant isothermal, pressure constant isobaric, মানে একটা বাকি থাকলো, that is your volume. So a volume is constant মানে isocoric process. তো এরকম হতে পারে যে আমি একটা বক্স নিলাম and I'm putting some balloon inside it which is occupying the entire volume. এখন যদি আমি এটার ভিতরে কনস্ট্যান্ট গ্যাস দিতে থাকি, the pressure will keep on increasing but the volume cannot increase because I have restricted its volume. The volume cannot increase. So this is something which is basically called as an isocoric process. এগুলো সব important because the syllabus will have Carnot cycle and all, and these terms we are going to use it there. Isothermal temperature constant, isobaric pressure constant, কেমন করে মনে রাখবে, বারের ইউনিট হচ্ছে প্রেশার, ইউনিট হচ্ছে বার, so third is isocoric মানে volume constant, and adiabatic is no exchange of heat. Now when we actually come to the reality, we might not be able to reverse a process, like say I want to go from A to B, ওকে, বাই সাম প্রসেস, মানে ধরো আমি একটা প্রেশার চেঞ্জ করে বা টেম্পারেচার চেঞ্জ করে ওই প্রসেস সিস্টেমে যাচ্ছি, এখানে ভলিউম V1 ছিল, আমি বিতে চলে গেছি ভলিউম V2. নাও If I release some gas, I can actually again come back to the same state. So if I'm going from volume, let's say V1 to volume V2, I can release the pressure and then come back to volume V1 again. So this is an example of a reversible process. But we have to remember that in thermodynamics, a process is only reversible if it is very, very slow. Okay, it is very slow. The change should be very slow. If it is changing very fast, then it may not be possible to get the exact same thing what we had before. So reversible process is kind of tricky in thermodynamic processes. But if we go into reality, the more than reversible process, there is something which we call as an irreversible process. So what happens usually is that if you're basically having a process, okay, if you're basically having a process and it keeps on changing and we cannot actually come back to the original state, we basically call it as a reversible process. So let's say I'm increasing the volume. If I'm increasing the volume, I'm increasing the disorderedness of a system. There are so many gas molecules which are moving randomly. আমি যত ভলিউম বাড়াবো randomness আরও বাড়বে. Like this also happens in case of universe also. Everyone say that the universe is ever expanding. So it is expanding. So if it is expanding, that means there is the randomness which keeps on increasing, and if the randomness keeps on increasing, we basically say it's entropy. Entropy is nothing but the measure of randomness, and this is something which keeps on increasing. Okay, something like a system which we have which generates a lot of heat. ধরো we have an engine, okay, and it gets used for kilometers after kilometers. So after 1 lakh or 2 lakh kilometer, people actually see that the engine has a lot of wear and tear. You cannot go back to the original state of the engine, because what happens is, because of the friction, there is a lot of loss, energy dissipation and all. You cannot get back that energy. So this is also an example of irreversible process. So heat and temperature are very much connected, but if there is some kind of energy that gets transferred because of heat, we basically because there is an energy transfer because of this temperature difference, we basically say that there is some heat transfer. Okay, এরকম হতে পারে I have a box, okay, and this is an adiabatic wall, no exchange of heat, আর এটার টেম্পারেচার হচ্ছে ধরো 90 ডিগ্রি, okay, and here the temperature, this is actually zeroth law of thermodynamics, এটা হচ্ছে ধরে নাও 30 ডিগ্রি। তাহলে আমি যদি এখন এটা খুলে দিই, if I open this up, I'm going to see that eventually this will be 90 plus 30 divided by 2, মানে total temperature হয়ে যাবে 60 degree. So there is a change in temperature, and this happens because there is energy transfer, and this energy is in the form of heat. So this is important. So heat যদি হয়, energy transfer, তার মানে work is also there, মানে এই equilibrium আসার জন্য there needs to be some work that needs to be done, and this is what is the work done example is. Okay, so first law of thermodynamics we are going to look into. Second law, third law, I'm not going to explain it here. Let's just start with the zeroth law of thermodynamics. So thermodynamics basically has got four laws. The first is the zeroth law of thermodynamics. The second is this is the zeroth law of thermodynamics. The second is the first law, second law, and first law and second law. So what happens usually is, when we think about zeroth law, we might say we feel a bit odd कि एटाके zeroth law কেন বলা হয়. So there are a lot of things, a lot of reasons behind this. There is no exact reason as such, but it may be because first law and second law were there, and after that the zeroth law came into the picture. Now zeroth law actually is more fundamental compared to the first law and second law, and that's why since already first law and second law was there, so it was named as zeroth law. Okay, so that is one of the notions that is there, but it is not a very complicated law to understand. There is no maths involved. Okay, there is some logic involved here. Let's say I have got a chamber. Okay, I've got a chamber, and then I have got a wall here, and then there are three systems here. Let's say this is A. Okay, it might be equilibrium in terms of temperature. Let's say this is B, and this is C. Okay, and this wall which we actually have is actually diathermic wall. Diathermic wall mane it can exchange heat. Okay, this is a diathermic wall, and this wall that we have, okay, this is an isothermal wall. That means, sorry, adiabatic wall. No, isothermal wall is not there. Adiabatic wall. Adiabatic wall mane does not exchange any kind of heat. So what happens is, let's say this is at some temperature, this is at another temperature, and A is also at another temperature. Okay, so in general, what will happen is, okay, let's take it in a, okay, just let me make it more simple here. Excellent. Let's change this. Okay, let's say Let's say this is your diathermic wall. That means this is exchanging heat. Okay, diathermic wall. And this is my adiabatic wall. Adiabatic wall. So what it means is that between B and C there is no exchange of heat, but between B and A and C and A there is exchange of heat. তো এখন যদি initially let's say A, B and C are all at different temperature, but after some time, since there is exchange of heat between A and B, the temperature of A, okay, the temperature of A will be actually equal to temperature of B. That's quite obvious because it a diathermic one, it will exchange heat, and also the temperature of A would be equal to temperature of C. This is quite logical. Okay, this is temperature of C. তার মানে what we can say is that the temperature of B must also be equal to temperature of C. So eventually what we see is that both all three A, B and C has actually achieved equilibrium. All A, B and C have achieved equilibrium. So this is the idea of zeroth law of thermodynamics. So if we just look into the statement, if two systems A and B are each in thermal equilibrium with the third system C, okay, A and B is equilibrium with third system C, or here we can say that two systems B and C are in equilibrium with the third system A, then A and B are also in thermal equilibrium with each other. Okay, তার মানে আমি যদি এইটার টেম্পারেচার এটা হবে, এটা হবে, তার মানে এই দুটো সেম থার্মাল ইকুইলিব্রিয়াম. Okay, so this is the idea of zeroth law of thermodynamics. And what happens here is that we are basically going to talk only about the thermal equilibrium. Okay, thermal equilibrium is very important. So if there is no heat transfer between the system, it means that they have achieved the same temperature. Achieve same temperature mane they are in equilibrium, which we call as a thermal equilibrium. Okay, so this is important, and this is actually the zeroth law. And there are a lot of reasons, as I said. I'm not going to discuss this, but zeroth law reason hobe je first law and second law came up, and then third law was more fundamental. I mean, zeroth law was more fundamental, so it was put before that. Okay, so numerical problems you might not be getting much. This is actually more logical. If I just read some questions here, see, three systems A, B and C are placed in contact under the following conditions. System A and system C are in thermal equilibrium. System B and system C are also in thermal equilibrium. Using zeroth law proves that system A and B are in thermal equilibrium. তাহলে এটা ভেরি সিম্পল, এ আর সি যদি থার্মাল ইকুইলিব্রিয়ামে থাকে, মানে আমরা এখন তো দেখেই নিয়েছি অলরেডি, the temperature of A would be in temperature of C. Similarly, B or C যদি থাকে তাহলে temperature of B must be equal to temperature of C. তার মানে temperature of A must be equal to temperature of C. Okay, and then so on. So you can just try to understand this and easily explain this. So these are some problems which are there. Okay, you can always check these. This is very simple. এখানে we discuss করছি না এগুলো, just this is just to understand zeroth law. It's quite simple. এইটা একবার দেখতে পারো. Two systems A and B are initially at different temperatures. ধরো 50 ডিগ্রিতে একটা আছে, and TB, which is let's say it's 30 degree. Now দুটোকে থার্মাল কন্ট্যাক্টে নিয়ে আসা হয়েছে, মানে থার্মাল কন্ট্যাক্ট মানে they can actually exchange heat. Okay, and they reach thermal equilibrium. What will be the final temperature of no heat is lost to the surrounding? So what happens is that in practically a system will lose heat to the surrounding. যদি হিটস লুজ করে তাহলে এটার অ্যাভারেজ নেওয়া যাবে না, এর জন্য এখানে স্পেসিফিক্যালি মেনশন করা হয়েছে that there is no heat lost to the surrounding. If there is no heat lost, then you can directly take the average. So if you take this 50 plus 30 and divide by 2, you can get 40. So you know that the final temperature of the system would be 40 degree. Now this seems to be quite obvious, but this actually comes from the zeroth law of thermodynamics. Okay, so this is again important. So there are some problems. Okay, I'll share the PDF, and then you can read or go through just to have an understanding of this. Okay, next is first law of thermodynamics. Okay, now first law of thermodynamics, before we come to that, there can be a number of questions like state first law of thermodynamics, what is the physical significance of first law of thermodynamics, what do you mean by internal energy, and so on. Okay, এগুলো সব first law সাথে connected more or less. So if you look into the first law of thermodynamics, this is also not very complicated. Like say I have got a system. Okay, I have got some system, and I have given some kind of heat to it. Okay, some kind of heat to it. Now as soon as I give some heat to it, it's not that the system will start heating up. The molecule has to start vibrating so that you can feel the heat from outside, and then it can actually do some kind of work. Okay, so let's say it heats up, and it gives that hot air outside, and that might be used for something else, to move a body or something like that. Okay, so when I give the heat, the first part of the heat is actually used to increase the internal energy. I keep on giving the heat, and the internal energy keeps on here increasing, and as soon as the internal energy reaches a certain point, this system will be ready for doing some work. So that means a part of it will be used to um, increase the internal energy, and then the remaining part of the heat will be used to do work. So this is the first law of thermodynamics, which is actually directly related to the conservation of energy. Quite obvious, heat মানে একটা form of energy. It is conservation মানে it is not lost, okay, not destroyed, only converted from one form to another, right? But এখানে আমরা দেখতে পাচ্ছি এখানে কোনো destruction হচ্ছে না, because a part of it is used to increase the internal energy, and then the remaining is used to do some work. So the change in the internal energy of a system is equal to the heat added to the system minus the work done by the system on its surrounding. Or we can say the amount of heat supplied to a system is used to change the internal energy plus the work done by the system. Okay, so you can say this is also a statement. Okay, so you can write it in this way or in this way. It's more or less the same thing. So work done and internal energy. এখন internal energy basically idea হচ্ছে যে it is basically a sum of kinetic energy and potential energy, okay, of the gas molecules. So this is what is written as terms of the mathematical form of first law of thermodynamics. Many places you'll directly find it out in the differential form as well. Okay, differential form যদি আমি লিখি তাহলে আমি লিখব dq, that means a small amount of heat is given to a system. It is used to increase the internal energy মানে du plus an amount of work done dw. So this is the first law of thermodynamics. Now what is my Q? Q is the heat added to the system, W is the work done by the system on the surrounding. Okay, এখন যে এইখানে একটু ট্রিকি আছে জিনিসটা, if we are basically saying it's a positive work, that means the work is done by the system. আর আমি যদি বলি it is negative, তার মানে work is done on the system. So you basically have a box and you want to move it, okay, and you are using a system to move it. That means the work is done by the system on the box, okay. But let's say the work is done on the system and not by the system, then it will be more or less negative work. Okay, so we're going to look into this later when we are going to talk about heat engines and all. Okay, heat engine was something which is like very preliminary to understand thermodynamics. যেখানে we give some heat, it generates maybe steam. Okay, we use coal to actually run steam engines and heat engines and all. Okay, and that will actually do some work, and that work will allow the train to move. Okay, so a simple example of a train maybe. So this is also directly related with this. So it is doing work to make the train move, so that means we are considering positive work. Okay, that is positive work. So the main technical word that we came across in first law of thermodynamics is actually called internal energy. Now, as I said, internal energy is actually a macroscopic property. It's not that I'm just going to consider one atom or one molecule and going to consider its kinetic energy and potential energy. No, we are going to consider the entire system. Okay, so that's why when someone says internal energy, the most important line is this: the internal energy is the total energy contained within the system. Okay, it will basically include the kinetic energy of the particle and the potential energy of the particle. Okay, so in general what happens is kinetic energy মানে there must be some velocity. There must be some velocity মানে যখনই একটা body motion এ থাকবে, that means let's say the particles are in motion, this will actually be due to their motion. So this will actually give you the kinetic energy of the system. But if we are considering potential energy, তার মানে because of the intermolecular forces. So let's say there are two gas molecules, and there is some kind of interaction between these two gas molecules, because of which neither of them can move too freely. Okay, there will always be some kind of interaction, intermolecular forces. Because of that, there will be some potential energy generated. So this potential energy, if we add it with the motion of the system, we're basically going to get the internal energy. Okay, so internal energy will basically change. Okay, মানে obvious, it's quite obvious that if you give some heat to a system, there will be change in kinetic and potential energy. So when heat is added or removed from a system, the work is done by or on the system. So যখনই এখন একটা সিস্টেমের উপরে there is some kind of work done, we always say that there is a change in the internal energy. Okay, and later on we are going to see that everything that we are going to consider is will be for an ideal gas. In reality, the relation between pressure and volume is not that simple. But if you're basically considering ideal gas, we basically write it down as PV is equal to nRT. Okay, that means pressure into volume is equal to the molar mass of the gas into molar gas constant into temperature. So this equation we are going to use again and again for an ideal gas, PV is equal to nRT. আর এখানে আমি যদি এই গ্যাস এইরকম টাইপের গ্যাস কনসিডার করি, then this U, which is the internal energy, will actually depend only on temperature. মানে if someone tells me that temperature is constant, there is no change in temperature, okay, the temperature is constant মানে temperature zero না, remember this, মানে আমি যদি temperature 60 রাখি তাহলে it will remain as 60, so there is no change in temperature. Delta T means T2 minus T1, so there is no change, so it is zero. So if there is no change in temperature, then the internal energy will also not change. That means delta U will also remain zero. This is something which is important here. This is something which you are going to use later as well. Okay, so internal energy will not change if the temperature does not change. Okay, so this is an important key concept from the first law of thermodynamics. Okay, similarly, we can talk about heat also. Now, heat we already know, the energy transfer due to temperature difference, already discussed. But আমি যদি একটা সিস্টেমকে হিট দিই, then we say that the heat is positive, and if the heat is released by the system, it is negative. Now this is why it is important, this is fundamental as well, because you might get questions, technical questions and confusing questions where they mention that the heat is positive or negative. If say positive, money heat is given to the system. If they say it's negative, that means the heat is being released by the system. Okay, so there are three ways of giving out heat. We already know this: conduction, convection, or radiation. Okay, next is work done, obviously, and a work done is again very important. So what happens is, usually we know work done is equal to force into displacement. Okay, this derivation might not be required, but then again we should know this is obviously simple, we already know it. Now work done is equal to force into displacement. Okay, now since we are talking about thermodynamics, pressure and everything is very important. So we know pressure is equal to force divided by area. Force divided by area. Force per unit area is pressure. But here we have force. The force is equal to pressure into area. So we can write it down as pressure into area into displacement. Into displacement. Okay. Now you consider a cylinder. Let's say this is a cylinder, and we are basically having a piston here. Piston. Okay, so what happens is, let's say this is a valve. Okay, this is a rubber valve, and we are actually going to move this downwards. So if we apply some pressure, this valve will move downwards. So if it's a 3D picture and if it moves downwards, you know that, let's say this has got an area A, this has got an area A, and after you give some pressure and this goes downwards, it will cover, let's say, a vertical distance of S, vertical distance of S. So if we multiply this area of the valve with the vertical distance, you're going to get the volume, because area unit of meter square, we already know that's the area. Logically you think about it in terms of three dimension. This is area, meter square. Our distance measure korchi mane we are going to talk about in terms of meter, let's say. So it will be meter cube. Meter cubed is nothing but the unit of volume. So area into the distance is nothing but volume. So we can write it down as P into V. Pressure into V. Now in general, if we say that a small work done, what will be the small work done, then we can say dW. Okay, dW is equal to PdV. PdV. Okay, the change in volume, if we are maintaining one constant pressure. Okay, so this is basically the idea here. So if this entire box has got a volume V, if we are reducing it, the volume changes, right? V2 minus V1. So this is the idea of work done. So this relation, this is W is equal to PdV, comes from the very basic definition of work done is equal to force into displacement. Force is pressure into area into displacement. Area into displacement is nothing but volume, so this is pressure into volume. So P is pressure, V is volume. So this relation we are going to use again and again, and this also gives me a different form of first law of thermodynamics. So what was the first law of thermodynamics? dq, okay, is equal to du plus dw. This is du plus dw. So this was our first law of thermodynamics. Okay, we've seen it. We can also now write it down as, we are going to use it later. We'll see that we have used this relation, du plus pdv. So whether you write it down as du plus dw or du plus pdv, both means it's, we're talking about the first law of thermodynamics. Okay, so there are two forms, these two forms, which are very important. So this comes from the first law of thermodynamics. Now let's go into these cases which I have already discussed, but there are certain points that you should remember, so that later on when we are actually doing it, you'll be able to do it more clearly. Okay? So if we look into some special cases, let's say I have got some process, like we already have discussed what are the processes that we know. This is isothermal process. Okay, isothermal process. Now in isothermal process, as I said, that the temperature does not change. The temperature change would be zero. Temperature is not zero, the change in temperature. But initially if it was 60, later on if there is also 60. And if you're basically considering an ideal gas, যদি temperature zero থাকে, তার মানে the internal energy also does not change, so del Q is also zero. So remember this relation. Okay, this will be more easy for us. dq, okay, is equal to du, this is our first law of thermodynamics, plus pdv. Let's start with this. Okay, or let's write it down as dw. Okay, তো এখন যদি temperature constant থাকে in isothermal process, this du will become 0. This du becomes 0. So if du becomes 0, simply dq is equal to dw, or q is equal to w. So we can say that q and w are equal. That means whatever heat is provided to the system, the entire heat is used to do work. Now this is only possible if it is an isothermal process. We're talking about ideal gases here. Okay, next is adiabatic process. Adiabatic process, there is no exchange of heat with the surrounding. Okay, so if there is no exchange of heat, that means we can say q is equal to 0. Okay, and if q is equal to 0, the change in the internal energy is equal to the negative of the work done. Okay, this is minus. So what happens usually is that if there is no exchange of heat, this part will again become 0. Okay, but then we are going to again have it as this dq is 0. So in this second case, what happens is, again we can write it down, this relation, dq is equal to du plus dw plus dw. Now in this case, if we say there is no exchange of heat, this will become 0 now. This will become 0. If this becomes 0, that means du is equal to minus dw. Okay, so that means the change in internal energy is equal to minus w. Physical significance is obviously there, but adiabatic process আমাদের qটা 0 হয়ে যাবে. Next is isochoric process. In isochoric process, what happens is, we know that the volume will more or less remain constant. তার মানে what is dw? dw is pdv. pdv. So a dv টা 0 হয়ে যাবে. There is no change in volume because it is an isochoric process. Delta v is equal to 0. So if this becomes 0, that means this dw will also become 0 in isochoric process. তার মানে it will be nothing but dq is equal to du. dq is equal to du. Okay, so this is what is happening in the isochoric process. Okay, finally we have got the isobaric process. Isobaric process means the pressure will more or less remain the 0, but if you look into this relation, there is no term where we are talking about change in pressure. It is dq is equal to du plus pdv. This is pressure, constant pressure, there is no change, there is not delta p, it is only p. Delta p will become 0. So that means if we consider an isobaric process where the pressure is constant, the law will remain the same. It will be dq is equal to du plus dw. It will remain the same, nothing will change, because delta p bole we don't have any term as delta p. Okay, so these are the 4 cases that we have, and based on these 4 cases, the first law of thermodynamics will have different forms, and we should know this. Okay, আমরা যদি 4 cases বুঝে নিই, that means heat constant, we know the law is different, temperature constant, law is looks different, isochoric process, the equation will look different, isobaric process equation will be same as the original one. Okay, so this is how we actually look into these special cases. So numericals are very simple for these kind of first law of thermodynamics. So you can just look into some questions here. See, a gas absorbs, okay, let me just read through this. Gas absorbs 100 joule of heat. okay, and does 40 joule of work. তার মানে you're giving a heat of 100 joule and it is doing 40 joule of work. Then that means that what about the remaining energy? The remaining energy goes into changing the internal energy. So we can easily find out what is the internal energy, which is nothing but 60 joule. Okay, simple process. Talk about an adiabatic process. We know adiabatic gas expands adiabatically and does 50 joule of work. Now for this kind of question, you have to understand that when it is adiabatic, মানে আমার delta Q is equal to 0. That means du is equal to minus dw. তার মানে you can directly consider this part to be 0. এখানে বলা হয়নি যে হিট ইজ গিভেন অর আউট অফ দ্য সিস্টেম অর গোয়িং ইন টু দ্য সিস্টেম। উই আর সেইং ইটস এন এডিয়াবেটিক প্রসেস, মানে হিট ইজ রিমেইনিং কনস্ট্যান্ট। তার মানে আমি কিউটাকে ডাইরেক্টলি জিরো নিয়ে নিতে পারি। ওয়ার্ক ডান দেওয়া আছে 50, you have to find out the change in internal energy, it will minus 50 of 2. Okay, so this is something which is important based on the above discussion that we have done. Because above discussion এ আমরা adiabatic, isothermal, isobaric and isochoric discuss করেছি. Based on that we can talk about the first law, and based on that we can actually do it. Okay, so what happens usually is if you're basically going to do numericals, we have to remember these conditions. Okay, we have to remember these conditions and then read the question, and then you can easily do it. So ধরো একটা question দিলো, a system is supplied with 500 joule of heat and it does 200 joule of work on the surrounding. You have to find out the total change in internal energy. Okay, change in the internal energy. So এখানে they have not mentioned anything. Okay, isothermal, isochoric, whatever, it's a basic system. So এখানে আমার তিনটে involved থাকবে, and then you can use the formula and find out what is the internal energy. Okay, let's see if we have anything else. Yeah, gas expands adiabatically, again the adiabatic process, so it is would be total 150. Okay, there is a question on isochoric process. Look into this. A gas absorbs 100 joule of heat while being held in a rigid container, no volume change. Volume change নেই মানে isochoric process, তার মানে আমার এখানে ইন্টারনালি বের করতে হবে। Isochoric process, no volume change means delta V is equal to 0. That means work done is equal to 0, because work done is equal to dw is equal to pdv. তার মানে work done is equal to 0, মানে dq is equal to du. That's it. So delta U, change in internal energy, already 100 joule দেওয়া আছে. You have to find out the internal energy, that will also be the same 100 joule. Means the entire heat supplied to the system is used to change the internal energy. There is no work done because I've kept the volume constant. That is the physical significance. Okay, isothermal process আমার du 0 হবে, there is no change in internal energy, so dq is equal to dw. work done দেওয়া আছে, you can find out what is the heat supply. Okay, এটা আবার মজার জিনিস, এখানে বেসিক্যালি হচ্ছে যে whatever heat you are giving, entire thing is used to do work, there is no change in internal energy. Okay, and this is something which is again something which is more or less ideal in nature, it might not happen. Okay, so these are some questions, and you can look into this. A system does 400 joule of work and its internal energy decreases by 200 joule. Determine the heat supplied to the system. So you can again do the same first law. Take this. Okay, so these are some questions you can always check. Okay, very easy, not that difficult. Okay, now we come to a bit of mathematical interpretation. So what happens usually is that you have to find out the work done in these processes. There are various processes. In all these processes we can actually find out the work done. Now as I said, what is work done? Work done is equal to pdv. And if we are changing the volume from, let's say, vi, initial volume, to final volume, okay, if you're changing it from initial volume to a final volume, then there will be some work which will be done. Okay, because let's say you have got a balloon. Okay, let me draw this. Let's say you've got a balloon and you are supplying some air to it. Eventually after some time the balloon will expand, right? The balloon will expand. So that means initially its volume was vi initial, and then it expanded and its volume become vf. That means vf minus vi is positive because vf is greater than vi. তার মানে in order to expand the balloon you have done some work. Now how much work you have done? For that we have to use such relation, w is equal to pdv, but we're changing it vi to vf, so we have to find out the total work done, so integration, right? We already know that dw. Okay, if you read some books on whatever notes you follow, you'll see that this would be the relation that will be used mostly. vw is equal to pdv. This is a small work done. Now if I want to find out the total work done, I'll integrate on this direction and I'll integrate on this direction. Initially there was no work done, and then I have done, let's say, a work w. initially there was volume vi, let's say the size of the balloon, and then I actually increase the volume to vf, so vi to vf, which is equal to pdv. So the work done is pressure into volume. Now this relation actually can be used to find the work done in isothermal process, isochoric process, isobaric process. Okay, we can directly do it. So for that we are going to use the relation for an ideal gas. Okay, so work done for an isothermal process. Now these relations are important. If you know all of them separately, you can directly use it to actually find out the work done or total work done in any kind of process. We're going to look into Carnot cycle later on. There also we're going to consider processes. We are going to find out the work done and add them up. So there I'm not going to do the maths because these work done we are already doing it initially. Okay, so let's see what is the work done in an isothermal process and how actually we can find it out. Okay, work done in an isothermal process. So if you're basically considering an isothermal process involving an ideal gas, the pressure that is there, okay, is PV is equal to nRT. We know the relation, and the work done relation was W is equal to PdV. তার মানে আমার যে প্রেশারটা আছে, we have to write it down in terms of volume. We can write it down easily. So what we can do is we can use this relation. PV is equal to nRT, মানে P is equal to nRT divided by V. Now if we replace this pressure here, we can do our calculation. So এখানে আমার বলছে isothermal process. Isothermal process মানে আমার temperature constant. So this temperature can be actually taken out of the integration sign. N is constant, R is also constant, which is actually molar gas constant. So nRT বাইরে এসে যাবে, it will be 1 by V dV. Now if you integrate 1 by V, it will be nothing but log of V, right? So it is ln of V. So if we do the integration of dv by v, this is very basic integration, dv by v, and this is vi, okay, and this is vf. So if we use the formula, it is nothing but ln, okay, ln v, and we are writing down the lower limit as vi, okay, and upper limit as vf. So what we can do is vi minus vf, so we can write it down as upper limit ln of vi, upper limit vf minus ln of vi. Now there is a log property, log of a minus log of b can be written as log of a by b. So log of vf minus log of vi can be written as log of vf by vi. So this is the work done in an isothermal process. If they ask you only to find out the work done for this is obviously an objective question, but this relation can be used in a number of places, like for example numericals and all. Okay, so work done is nRT ln of vf divided by vi. So this is the work done in isothermal process. This may not be the same for other processes, so let's just have a look. When we're basically considering an adiabatic process, and if you're considering an ideal gas, the relation is not PV is equal to constant. See, for an isothermal process, temperature is constant, nR is constant, so that means pressure into volume will remain constant. When we basically consider an adiabatic process, whenever we are considering an adiabatic process, the relation is PV to the power gamma is equal to constant. Okay, and gamma is actually nothing but called as the specific heat ratio. We're going to look into what is specific heat ratio later, but it can be written as Cp by Cv. That means the specific heat at constant pressure by specific heat at constant volume. So what happens usually is that if you're giving some kind of heat to a system, there will be a rise in temperature. Okay, so how much heat you should give for a system to raise its temperature by, let's say, 1 degree, okay, is something which is connected with the specific heat. Okay, so maybe I keep the constant volume and I'm going to give some heat to raise the unit temperature of a unit substance, maybe 1 gram of substance by 1 degree centigrade. That is called specific heat. So it may be at constant pressure, it may be at constant volume, and if you take this ratio of Cp by Cv, we get something which we call as gamma. Now you have to remember that this Cp by Cv, or ratio of the specific heat, is actually constant for different systems. Okay, if you consider different system, it has got a different gamma value. Okay, so this PV to the power gamma is equal to constant is the relation when we are basically considering an adiabatic process. So if we basically consider an ideal gas law, nRT by V, we can actually use this relation But here we have got is equal to constant C, let's say. So that means the pressure is C divided by V to the power gamma. Now relation will become C divided by V to the power gamma. So in place of pressure, we have to write down C divided by V to the power gamma. Now this again can be done, derived. Okay, so C divided by V to the power gamma. If we do the integration, we are going to get this. Okay, so I'd like you to try this integration. Okay, because it's not like simple of ln, because it is dv by v to the power gamma. So you can use the relation of integration of x to the power n dx, x to the power n plus 1 divided by n plus 1. So if you use that relation, this would be minus gamma. So minus gamma plus 1 divided by minus gamma plus 1. So it will be 1 minus gamma. So below it will be 1 minus gamma, above it will be v into 1 minus gamma to the vf vi. So now if we use the relation pv to the power gamma is equal to constant, we can actually simplify it to this relation. This derivation maybe I'll show it to you in the next class. Okay, so you see the work done in an adiabatic process is different. Okay, you can stop here as well. This is also the work done relation directly. Okay, so that means I can take this. Okay, what happens usually is if you basically consider that pv. Okay, anyway I can show it to you this maybe. Yeah, if I say that pv to the power gamma is constant, pv to the power gamma is equal to constant. Okay, constant. Okay, now that means it simply means that p1, if you take the multiplication of p and v to the power gamma in any situation, you're going to get the same value. That means p1 v1 to the power gamma is equal to p2 v2 to the power gamma and so on, p2 v2 to the power gamma and so on, and that will always remain as constant. Okay, so this idea was actually used here. Okay, this constant is p1 v1 to the power gamma, or we can say pi vi to the power gamma is equal to p2 v2 to the power gamma and so on. So in place of this c, I can write down this relation and then I can take it final minus initial. Okay, so that way also we can take this. Okay, this is the basic idea, and if we put it here, we are going to get this relation. Now you multiply it, vi to the power gamma or vf to the power 1 minus gamma, or you can also vi to the power 1 minus gamma. Okay, so if I multiply this term, 1 gamma minus 1 niche ache, so I can take it as 1 minus gamma. এটাকে রিভার্স করে দিলাম, এটা vi, এটাও vi, to the power gamma, এটা minus gamma cancel হয়ে গেল, it will be pi vi. Okay, so this would be for vi. Another term I can have for vf, so I can multiply it, it will be pf vf and so on. Okay, but we can take this to be the main relation for work done in case of an adiabatic process. Okay, so I think we can stop here.